Chapter 3, Polynomial and Rational Functions. Section 3.1, Quadratic Functions. Having studied functions in general in Chapter 2, in Chapters 3 and 4 we'll be looking at some specific classes or families of functions. The focus in Chapter 3 is in general on polynomial functions and then also rational functions. But we'll begin with a more specific type of polynomial function, which is the quadratic function. So recall the squaring function f of x equals x squared, whose graph is a parabola. This is one of the basic functions that you needed to know about in Chapter 2, especially for the purposes of graphing transformations. This is the simplest example of a class of polynomial functions called quadratic functions. So the squaring function is the simplest quadratic function. So what is a quadratic function in general? A quadratic function is a function of the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. For the squaring function, we would have a equal to 1, b equal to 0, and c equal to 0. We would also call such a function a second degree polynomial function because the highest power of x that appears is 2. So there must be an x squared term to have a quadratic function. Now let's look at some facts about quadratic functions. Fun facts, that is. First of all, the domain is the set of all real numbers, minus infinity to infinity. So quadratic functions, unless explicitly stated otherwise, we'll assume they have an unrestricted domain. The graph is a parabola, which is what we saw with the squaring function. So all quadratic functions have graphs that are parabolas. The parabola opens upwards if a is positive and downward if a is negative. So you can see below there a parabola with a greater than 0 or positive and a parabola with a less than 0 or negative. So the parabola with a positive opens up, the parabola with a negative opens down. The turning point of the parabola is called the vertex. The vertex is either the lowest or the highest point on the parabola. So I'll identify the vertex on each of the parabolas below. This point right here. And in this case, the vertex is the lowest point, so it's yielding a minimum value for the function. This is something that we'll have to look at a little bit later in the notes, this relationship between the vertex and minimum and maximum values. And then in our second parabola, the vertex is the highest point, and so yields a maximum value. So the turning point of the parabola is the vertex. In the second graph, you see how the vertex is right on the y-axis. Next point, every parabola is symmetric about a vertical line called the axis of symmetry that passes through the vertex. So we sometimes represent the axis of symmetry as a dashed line. So let me show you what that would look like here. So it passes right through the vertex, and if we look at the parabola in reference to that vertical line, we see that the parabola is symmetric about that line. So this is the axis of symmetry. For the second graph, the axis of symmetry, notice, is the y-axis itself. This is actually the case for the squaring function. The y-axis acts as the axis of symmetry, and in such cases it means that you're dealing with an even function, because even functions have graphs that are symmetric about the y-axis. So here the axis of symmetry is the y-axis itself. Next point, the y-intercept of the parabola is the point 0, c, again assuming we have a function of the form f of x equals ax squared plus bx plus c. In other words, what we're saying here is that f of 0 equals c. And if you look above, it's not shown here in the video at this point, but if you look at the function f of x equals ax squared plus bx plus c, if you substitute 0 for x, then you get f of 0 equals c. So that means that the point 0, c is on the graph of the parabola, and that's going to be the y-intercept of the parabola. Next point, the greater the value of the absolute value of a, that is, here we're thinking about the value of a without regard to its sign, the narrower or more vertically stretched the parabola. So a is a vertical stretch factor, and the greater the value of a in absolute value, the more vertically stretched the parabola. Therefore, the parabola is going to look narrower as the absolute value of a increases, and wider as the absolute value of a decreases. And then final bullet point, the graph of a quadratic function of the form f of x equals ax squared, of which f of x equals x squared is one example, that would be a equals 1, is a parabola with vertex at the origin and symmetric to the y-axis, in other words, an even function. So for example, if you had f of x equals negative 4x squared, then you would recognize that as a parabola with vertex at the origin and as an even function with y-axis, whose graph has y-axis symmetry. Let's look at a few graphs of simple quadratic functions and relate some of the ideas we've just talked about back to the transformation rules we studied in Chapter 2. On the same set of axes graph, first of all, y equals x squared, which is actually already shown, and y equals x squared minus 4. Well, we should know that y equals x squared minus 4 is a translation of the graph of y equals x squared 4 units down. So this is a vertical translation of the graph of y equals x squared. So let's plot some specific points. For example, the point on y equals x squared at the origin, that is the vertex, is now at 0, negative 4. Another point we might plot would be the point at 2, 4. The point at 2, 4 would now be at 2, 0. Again, 4 units down. And then similarly, excuse me, getting some windows popping up here. Another point at, so we have a point at 2, 0 and a point at negative 2, 0. And what we would see is something like this. Now, it would appear that the parabolas get, well, in fact, they do get closer and closer together. But in terms of the shifting of the graph, every point on the graph of y equals x squared is getting shifted by the same amount, even though obviously the graphs get closer together. Individual points are all moving down 4 units. So don't let that make you think that some points are moving less than others. They're all actually moving down the same distance of 4 units. Okay, next one, we again already see y equals x squared. What about y equals 2x squared? Well, again, you might recall that the 2 here would act as a vertical stretch factor, doubling the y-coordinate of the original point. So the point at the origin with y equal to 0 would stay at y equals 0. What about the point at 1, 1, right here? Well, now that would be at 1, 2. You would double the y value. What about the point at 2, 4? Well, now that would move to 2, 8, again doubling the y value. And then similarly for points on the left-hand side of the y-axis, we would see the same sort of thing occur. And so you see some points are moving more than others. Some points aren't moving at all. For example, the point of the origin stays where it is. So what we get is a vertically stretched graph, something like this. And to be vertically stretched for a parabola is identical to making the parabola narrower. So this is the effect of the multiplication by 2 in front of the x squared. In this case, a is equal to 2. And that is giving you a vertical stretch or a narrower parabola. Let's look at C. Y equals x squared and y equals negative 1/2 x squared. This is similar. Here we have a equal to negative 1/2. This is a vertical shrink factor. Every y-coordinate will be cut in half. And in addition, we have a negative sign, and that is going to give us a reflection so that the parabola opens down rather than up. So we have to take both of these things into consideration. If we plot some specific points, point at the origin will stay at the origin. We're multiplying it by negative 1/2. The y-coordinate is multiplied by negative 1/2, and negative 1/2 times 0 is still 0. If we take the point, say, at, let's look at 2, 4, we're going to cut that in half and then reflect it across the x-axis. So cutting it in half, we would get, we would go from 4 to 2, and then we would take that across the x-axis to get negative 2. So we'd have the point at 2, negative 2, and then another point which is actually not appearing on the graph of y equals x squared here would be 4, 16. That would move to 4, negative 8. Half of 16 is 8, and then we reflect across the x-axis. And then we would have points also at negative 2, 2, and negative 4, negative 8. And then you can see that the parabola here is opening down. And is wider than before. So here we have a negative value of a, so the parabola is opening down. And because in absolute value a is 1/2, the parabola is opening wider. It's a vertical shrink factor, and the parabola opens wider than before. So with A and B, A was positive and the parabola is opened up. With C, A is negative and the parabola opens down.